Hello everyone, this is Dr. Chen. We're going to talk about the first part of DC circuit. So let's first remind ourselves what are the elements of the circuit. So we have power supply, right? It can be a battery or something else. Next, the DC supplies we used in the lab. And then we use a symbol that has one longer line and one shorter line to represent EMF, power supply in the circuit. The longer line represents the positive end. Then have a resistor. How do we represent a resistor? So it's basically a zigzag line. That's a resistor. We have capacitor. Capacitor represented by two parallel plates. So they should have roughly the same length comparing to EMF. Then straight lines are for wire, light bulb, switch, ground, voltmeter, ampere meter, and ohmic meter. This is a typical DC circuit. You see, how do we measure the potential difference between 2 points in a circuit? You just have positive end of the voltmeter on one end, negative terminal of the voltmeter to the other end, and it will give you the potential difference between 2 points on the circuit. Now we have some voltage rules for different circuit elements. Now first, wire. If you have a metal in equilibrium from Gauss law, we know the entire metal become equal potential surface. So you can imagine if you have a wire and there's nothing connected to the wire, is an equal potential surface as well. So any 2 points along this wire give you the same potential difference of 2 points at 0. Now if you have a resistor, on the other hand, if there is a current going through this resistor, we have Ohm's law, V equal IR. The potential difference between the resistor, the potential difference over this resistor equals current going through the resistor times the resistor of itself. Now, make sure that when you use when you use Ohm's law, V equals IR, which is also the resistor rule, that you understand that the potential V is the potential over the two ends of this resistor. And also, now we say the potential difference is I times R, then how do I know which point is higher potential, which point is lower potential? For such a question, the answer is that you have to follow the direction of the current. And we know potential is decreasing over the current. So in this case, you see B is a higher potential compared to C because current is flowing from B to C for this resistor. Then we have the switch rule. If switch is closed, then this just becomes a wire, so the potential difference between the 2 points is 0. You keep the switch open. There's no current going through. And the potential of E and F is the same, potential of D and A is the same. So VED equals VAF should be epsilon. And if you measure the ideal potential, it's just epsilon. Now let's show what is a series connection and a parallel connection. So this is your positive, well, you can call this one positive because it looks like they use red, usually we use red cable for positive. This is my current. So in series connection, this is series connection on the top. the current only has one way to flow in a series connection. And now if you have a parallel connection like this one, parallel, you have a current that goes in here, and this current can go this way or go this way. This is I can call this one I1, this one I2, and then here I want I2 merge and give you back I again here. So this is a difference between parallel connection and a series connection. Parallel connection, the current can split. For a series connection, there is only one path for the current. So that's a difference. And we want to know if you put some resistors in series, what will be the equivalent resistance, and how to define equivalent resistance. So basically, you connect R1, R2, R3 in series like this, and this is our battery. So what we want to find out is if you apply a battery which has potential VAB on R1, R2, R3 connecting in series, what's the current going through point A? So I is VAB divided by, now you're going to treat all the three as one resistor with resistance R equivalent. So if you use this equation, you can find out R equivalent is defined as the potential you apply, VAB, and what would be the current going through point A, or you can also say it's current going through point B. They should be the same. So keeping in mind that we want to find out VAB over I. And how do we find that? How do we find that? We need some information. We need some more information. We need to figure out that what's the relation between the potential over R1, R2, and R3, and what's the current going through R1, R2, R3. Let's first think about the current. So if you have a series circuit, and we said the current cannot split, so there's only one way the current can go. And current is made up of electrons or other positive charge, and mostly electron. Electron going only one way, and an electron cannot escape this circuit. So the current, if you can imagine, the current should be everywhere the same. Current should be everywhere the same. Then how about the potential? This is my VAB. This is my V1. This is my V2. This is my V3. And by looking at this circuit, we should understand that VAB equals V1 plus V2 plus V3. So we have two conditions for series connection now. Do we? We have two. So we have VAB equals V1 plus V2 plus V3. And then we also know I1 equals I2 equals I3 equals I. Let's call it I. Current is everywhere the same in series circuit. So current going through R1, current going through R2, current going through R3 are the same. Then I can apply Ohm's law. I1 is I1 times R1. V1 is I1 times R1. This is Ohm's law. V2 is I2 times R2. V3 is I3 times R3, and they all equals to I. So it's I plus I1 plus R2 plus R3. I bracket R1 plus R2. I3. And now I do know R equivalent was defined as VAB over I, and now I can solve it. I find it is R1 plus R2 plus R3. So the equivalent resistance of three resistors connecting in series is you just add up the resistance together. This is a more general equation even if you have more resistors. If you put resistors in series, the equivalent resistance is just the sum of them. Okay, now we move on to find out the equivalent resistance for resistors in parallel. We have R1, R2, R3 in parallel connection to each other, and we apply a VAB. What will be the current going through here? We also need to understand what's the relation between the current and potential for R1, R2, R3. Now this time currents are not everywhere the same. Instead, if you have a water current, right? So this is kind of a parallel connection. This is going through this network, this is going through this network. You can totally change this to an electric circuit if your water is carrying charge per volume. Then this is a total water current. This is water current 1. This is water current 2. And of course, you can imagine I equals I1 plus I2, right? And this is the same thing. You have total current here split to A2 split to A3. Here you should have the total current equals to the sum of current going through two different resistors. And then we have the we need to think about what's the potential. What's the potential on this? So this is VA, this is VB, and we use wiring rule. We find V1 is VB, V2 is VB, V3 is VB. So let's call V1 equals V2 equals V3 equals V. So in a parallel connection, the potential difference over this parallel condition for each circuit element is the same. And then current, let's say this is total current I, this is I1, this is I2, this is I3, and we should have I equals I1 plus I2 plus I3. And I equals VAB over R equivalent, and I1 is V1 over R1 from Ohm's law. I2 is V2 over R2 Ohm's law. I3 V3 over R3. And now I know VAB. This is VAB equals V1 equals V2 equals V3. They all equals to V, so V so every term has V. We can just divide a V from both terms, so we find out the equation we are looking for. The equivalent resistance of resistors in parallel to be given by this equation. Now we see if you have two resistors in parallel, you have one R equivalent equals 1 over R1 plus 1 over R2, just two. and we can calculate as this. So maybe this one is more helpful for you if you're going to do calculation on the exam. So now we will do a few examples using the equivalent resistance equations we just derived to do our calculation. So we have three resistors connecting like this as a triangle, and then we want to find out what's the equivalent resistance. What's the equivalent resistance of if you connect your battery over the two different points of A and B? So basically what it says, we apply a 35, right? 35 volt battery on A and B. What would be the net current going through here? So maybe we need to redraw this diagram a little bit to help us understand. So you can see your positive end connected to A. And then you see from your A, it splits. And the one path goes through the 15 ohmega resistor. And it goes to B if you go over 15 on the other side of 15 point B. And then from A you can also go 20 ohmega and then you get to point C. You keep going, you see C, you need to go over this 10 and then goes to B. Now these 2 points are the same points, so we join them together. And then what do you connect the B to? You connect the B to the negative end of this epsilon equals 35. So you can also redraw this one. Apparently is this resistor and those resistors in parallel. So you can redraw it a little bit. Looks like 15 and 30 ohmega in parallel, right? So if you put 20 and 10 in series, the equivalent resistance is apparently 30. So the equivalent resistance of everything is the equivalent resistance of you have 15 and 30 connecting together. So what is 15 and 30 connecting in parallel together? 1 over I equivalent equals 1 over 15 plus 1 over 30 equals 33. So equivalent resistance is 10 ohmega. So the I going through here should be 35 of R equivalent is 35 over 10, 3.5 amperes. And that's the answer. What's the total current going through if you connect it 35 epsilon to point A and B? Now you can follow what I did for other different connection, and the procedure is the same. It's just that the numbers will be a little bit different, right? Okay, example 2. You have R1, R2, and R3. We know the resistance, and now we know its ideal EMF. The ideal battery has epsilon, which we don't know, but we do know is I going through R2. It's called I2 is 4 amperes. So we know R1, R2, R3. We know I2. We want to find out I1, I3, and the epsilon of the battery. So here I know I2 is 4 and R2 is 6 omega, I1 is 3 omega, I3 is 5 omega. Okay, So let's look at R1 and R2, how they are connected. Parallel, right? Parallel. When R1 and R2 connected in parallel, so I should know V1 equals V2. And can I find out what is V2? I know R2 I2 equals 4, and Ohm's law, V2 is I2 R2, 24 volts. So V1 is 24 volt as well. And I know R1 equals 3. V1 is 24. What is I1? I1 is V1 over R1, 8 amperes. So this is 8 amperes. Now do I know what's the current going through R3? 8, 4, here it must be 12. So I3 is I1 plus I2, because all the current merge here and give you I3. So I3 is I1 plus I2, 4 times 8, 12. Okay, now I know I3 is 12. Can I find out what is V3? I3 times I3, 60. So epsilon should equals to the potential here plus potential here. Epsilon equals V1 plus V3 equals 84 volts. That's the answer. Okay, the last example. You have the circuit like that. What we know is P1 is 15 volts, and the total current here is 3.5. Current here is 2. We want to find out R1, R2, find out the epsilon, find out the current going through 10 ohms. Okay, so first let's find out R1. P1 should be I1 squared times R1 equals 15. So R1, and I know I1, right? I1 equals 2. So R1 is 15 divided by 2 squared is 3.5 ohms. And also ask what is R2, but we're not ready to solve it, so I will just leave it here. And let's see what's the next question. We want to find out EMF. Okay, I think we can do that, right? So this is what's epsilon. And this point and this point equal potential. This point equal potential. So epsilon should equals to V1 equals I1 R1 Ohm's law. I1 is 2, R1 is 3.5. No, not 3.5, sorry. 15 divided by 2. 15 divided by 2 is 7.5. So 15 divided by 4 is 3.75. Okay. I1 is 2. R1 is 3.75. Is 7.5 volt. Epsilon is 7.5 volt. Now it asks us to find out what is current going through here and current going through here. Let's call this one I2, this one I3. So I can very easily find out what is I3, right? I know the potential of R3 is also epsilon over R3, which is 10, so it's 7.5, 10, 0.05 amperes. I find I1 is 2, I3 is 0.75, and the total current is 3.5. But you can see here, this is your total current that is split into I3, I2, and I1. So I should equals to I1 plus I2 plus I3, and then you already found out what it is. It's given I1 is 2, I3 is 0.75. So I can find out I2 is 0.75 as well. Okay, now good. I found I2 and then know epsilon, which is potential over R2. I'm ready to find out what is R2 now. R2 is epsilon over I2, which is also 10 omega. Okay, last question. What is the power of the battery? It's just epsilon times I. And it just has to check what's the power at all the resistors is just I1 square R1, I2 square R2, I3 square R3, and you plug in all the numbers we found, you find it also 26.25. So the power consumed by the battery equals the power consumed by the resistors. So we have energy conservation. Hopefully, this lecture gives you more confidence to solve a problem on DC circuit with parallel and series connection of resistors. I'll see you next time. Thank you.